The Moon is Earth's only natural satellite and its closest neighbor in space. Most likely, the Moon was formed when an object the size of Mars collided with our planet. The catastrophe occurred billions of years ago. It turned the Earth into a molten ball and put a huge mass of matter into orbit, which cooled and took a round shape. The crater ball now orbits around our planet, causing the oceans to ebb and flow. The Moon is just over a quarter of the size of the Earth. This makes it the fifth largest natural satellite in the solar system. The Moon has several phases. For example, new moon, full moon, crescent moon, first quarter, and last quarter. But whatever the phase, our neighbor is hard to confuse with any other space object at night, and sometimes even during the day. But imagine waking up at night and seeing that the Moon looks different than usual. It seems brighter and more. However, in the case of a half moon, the changes are not as noticeable. You go back to bed without even realizing that Mercury has taken the Moon's place. The surface of Mercury, the closest planet to the Sun, resembles a lunar landscape. It's full of meteor craters. Mercury is no more than 2/5 the size of the Earth. It is, however, slightly larger than the Moon, and so the planet Earth has a greater influence. The nights are lighter, the tides are stronger. The lunar cycle, the period during which the Moon, or rather Mercury, goes through all its phases, is shortened by 14 hours. But overall, this substitution will not drastically affect the state of our planet. And what about Venus? What if our famous satellite replaced the third brightest natural object after the Sun and Moon? Venus is often called Earth's sister, as they are almost the same mass and size. In our sky, Venus would be the same size as the Earth observed by the Apollo crew from the surface of the Moon. The home star will be much brighter than the Moon. First, the planet reflects 6 times more sunlight. Second, it takes up at least 16 times more space. This is why nights on Earth become bright as early twilight. If you looked at Venus, you would notice fuzzy curls in its yellowish white cloud. Venus probably wouldn't be a satellite of Earth. Both planets would orbit around their common center of mass, and that orbit would be pretty weird. If Venus were moving at the same speed as the Moon, the planets would collide in the near future. Oh no, well, it's time to move on. If Mars were instead of the Moon. You're sure to spot it because of its reddish disk and the planet's size, which is twice the size of the Moon. You wouldn't even need a telescope to admire the unusual colors and dark spots on the planet's surface. And even if you don't pay attention to the red planet, you are bound to sense that something is off. Mars is half the size of Earth, but many times the size of the Moon. When a small spatial object is replaced by a larger one, it upsets the delicate balance. If you are unlucky enough to be on the coast when Mars replaces the Moon, you will have to evacuate quickly. The planet's impact creates strong waves that crash onto the coast like a giant tsunami. Mars reflects more sunlight than the Moon. Nights get lighter. Landscapes take on an eerie reddish hue. But you can use a telescope to admire Olympus, the tallest mountain in the solar system. Mars is not large enough to radically change Earth's orbit. Over time, however, the two planets will probably begin to orbit around each other, forming a double planetary system. And because Mars is so close, traveling there becomes a reality. It's time to think more broadly. If Jupiter were to replace the Moon, Earth would cease to exist as an independent planet. It will become a satellite of the largest planet in the solar system. But there is some good news. In this case, people will have the opportunity to see the magnificent sky. Jupiter was incomparably larger than the Moon, and the giant striped ball stretched across the entire visible horizon. If there were time, you could admire the yellow, brown, red, and white clouds floating in Jupiter's atmosphere. Unfortunately, the gas giant's gravity would immediately cause earthquakes, volcanic eruptions, and tsunamis. The Earth's crust and mantle would begin to stretch toward Jupiter, and the Earth would tear apart. The planet would shrink and stretch in different directions by 90 meters. Unfortunately, Earth's speed is only 10% of the speed needed to stay in Jupiter's orbit. That's why our planet collided with the gas giant in less than 24 hours. But we're not sad. If Saturn had been there instead of the Moon, it would have been an unforgettable sight. The planet is more than 35 times the size of our satellite. The golden orb will be at an 18-degree angle in the sky, and the famous rings would stretch from horizon to horizon. Earth would be a little farther away from the gas giant than its satellite Dione, and since Saturn is so much more powerful than our planet, it would be Earth. Unfortunately, Earth's rotational velocity will not be enough, and we will collide with Saturn in a few days. But before we can enter the planet's atmosphere, we'll have to pass through its beautiful rings. They're made up of debris from comets, asteroids, and broken satellites. Yes, the journey ahead will not be easy. And don't forget that Earth has to revolve around Saturn's satellites, and there are 53 of them. What if the collision didn't happen, and Earth became the 54th satellite? Then the gas giant's gravity would cause violent tectonic changes throughout the Earth. The dear planet would be torn apart, and eventually there would be nothing left of it. Not a very positive result either. Both Uranus and Neptune are ice giants. They're about the same size. More than on Earth, but less than on Saturn and Jupiter. Both planets are covered in ice and have a beautiful greenish-gray color. If one of them replaced the Moon, the consequences would be the same. So, let's flip a coin. Okay, let's see what happens if you ever see Neptune in the sky. Neptune is 14 times larger than the Moon. The planet would look like a huge blue balloon. And not just during the day, but at night as well. You think Neptune is 15 times larger than the Sun, and you regularly experience solar eclipses. After the Sun disappears behind Neptune, our planet will go into total darkness for more than half an hour. Neptune's mass is 17 times that of Earth, and its gravitational pull is much stronger. So our planet would be a satellite. Yes, one more time. And it would orbit around Neptune at a slightly greater distance than its largest satellite, Triton. What's more, in this case, Earth could end up colliding with this cosmic object. But suppose we were lucky enough not to encounter any of Neptune's satellites. However, even without that, we'd have enough problems. Earth's waves will be 1,000 times stronger than the Moon's. Neptune's gravitational pull would not tear Earth apart, but it would warm our planet. Seismic activity would gradually increase, causing earthquakes and volcanic eruptions, and we would probably lose our internet. Use your imagination to draw two parallel horizontal lines. Now, connect them at any point in two different ways. A vertical line going straight up from the bottom line and a diagonal line. Which one is shorter? Of course, vertically. This is the shortest way to connect the top and bottom lines. And that's the most basic answer to our question. It's easier and faster to go straight up into orbit. The bottom is the surface of the Earth. Our planet is a complex mixture of all kinds of matter combined into an impressive mass, almost 6 sextillion tons. It's about 6 trillion billion, usually a big pile of zeros. Essentially, all of this mass acts as a giant magnet that, among other things, allows the Earth to retain what we all know as an atmosphere. The top line is the boundary of Earth's atmosphere. All of the above is planetary orbit and space, but the atmosphere itself is also full of matter. It's a mixture of gases that has its own density. When the shuttle is launched, the entire mass of this gas constantly compresses it, causing friction and slowing it down considerably. Going through a vacuum is like cutting through air, and going through the atmosphere is more like cutting through jelly. Grapes are like strawberries. It takes a lot of energy and strength to get through it, as you experience the tremendous pull of Earth's gravity. Airplanes don't suffer as much when passing through the atmosphere, because they use its density to lift off the ground and maintain altitude. Two things that help them do this are engine thrust and the shape of the wings. The wings of an airplane cause the air in front of them to separate into two streams. Naturally, behind the wings the jets merge, but their shape makes the reverse flow faster. The faster the air moves, the more it loses density. This means that the flow under the wing is denser than the flow above. This causes the airplane to gradually rise upward. Essentially, the wings allow the airplane to glide through the air. Of course, this wouldn't be possible without the tremendous force pushing the car forward. That's what stakes are for. Just to get off the ground, the airplane has to reach a tremendous speed. The speed required depends largely on the type of airplane. 96.5 kilometers per h for light aircraft and about 241 kilometers per h for jets. A Boeing 747 needs just under 3 tons of fuel to take off and reach an altitude of 3 kilometers. This may sound impressive, but let's take a look at the space shuttle. The first thing that catches the eye is the beautiful short wings, which would be useless in a horizontal plane. On the other hand, more massive wings are useless in a space vacuum. They are also difficult to make strong enough to withstand gunfire. The small wings of the space shuttle serve only one purpose: to land safely so that the platform can be used for future missions. They would have to be large enough to prevent the shuttle from spinning uncontrollably as it descends through the atmosphere and delivers it to Earth, since no engines are used during descent. Spacecraft engines are completely different from aircraft engines. Aircraft engines need air from the atmosphere to operate. Apparently, shuttle engines don't need it because atmospheric air is hard to get in space. That's why the shuttles use rocket engines. To see what a rocket means in this case and how it all works, inflate and release a balloon. It spins until it runs out of air because it moves in the opposite direction to the air coming out. For takeoff, a rocket engine must create enough thrust and burn the required amount of fuel. In fact, the space shuttle needs so much fuel to achieve thrust at launch that it can't make do with just three engines. It would require 2 additional stationary rocket boosters and a separate huge fuel tank that is emptied during the final stage of the launch. And the shuttle will only be able to go into orbit with enough power. The shuttle's power with 3 engines and 2 boosters is about 3.5 million kilograms of thrust. To achieve this effective thrust, the external tank contains about 725,000 kilograms of fuel. And to control flight, those 3 engines must have a staggeringly complex design. Would it be possible to get the shuttle into orbit if we modified it to use the atmosphere like airplanes? Unfortunately, the answer is no. Even more fuel would be required to maintain the necessary speed at a distance from the diagonal launch trajectory. The fact is that even if the airplane reaches the upper atmosphere, the Earth still won't let it go. To leave the atmosphere, any object leaving the Earth must be fast enough to cross a point called escape velocity. This is necessary to overcome the planet's gravity and get the object into orbit. The rotational speed of our planet is 28,000 kilometers per hour. Obviously, this is well above the speed of sound and many times the speed of an airplane. Now, try to imagine an airplane flying at that speed and how much fuel it would need. It must also be strong enough to not break. The cost and complexity of the technology would be simply unrealistic. With the possibility of the shuttle becoming a thing of the past, scientists and engineers are looking for a better solution to reach orbit beyond it. One such idea suggests that in the future, people will be lifted into space in a huge space elevator. A space elevator is the concept of a huge tower that reaches an orbiting satellite, moving in time with the rotation of the Earth itself. The tower would have to be about 35,400 kilometers high, and it would have to be made of an incredibly strong material, carbon nanotubes. The platform inside the tower would have to be controlled by electromagnetic conveyors. The journey from Earth to the satellite takes only 5 hours. Such a megastructure would provide faster and safer access to space. However, carbon nanotubes were not strong enough to build such a large tower. Therefore, the search for the ideal material is still ongoing. Another project using a similar approach is called the space tram. The structure needed for the project is not that big, but it is still impressive. It is a vertical vacuum tunnel that lifts the shuttle by magnetic thrust. The air doesn't slow it down, and an electromagnetic force pushes through the tunnel, providing acceleration until the shuttle takes to the sky at near-space speeds. Such a shuttle would weigh less, since it wouldn't have to carry as much fuel, but there is still no word on how a human can withstand such acceleration. The crew can then be turned into a pancake. If such ideas seem strange to you, and they are, prepare for the latter. People can use airplanes to get into orbit. No, I wasn't lying to you. The car itself can't go into space, but it can act as a launch pad. Even better, right? A special aircraft with a wingspan of almost 122 meters and capable of reaching heights of more than 10 kilometers will be created for this purpose. Small shuttles launched from such an airplane wouldn't have to go through much of the atmosphere and would have an easier time overcoming Earth's gravity. Richard Branson is already working on this solution as part of the Virgin Galactic program, which takes passengers to the edge of space. Very often the world around us seems ordinary and commonplace. However, if you just look a little closer, everything turns out to be quite different. For a long time, we thought that our solar system was just one of many star systems in the Milky Way. There are rocky planets. Like everywhere else, there are also gas giants. But soon astronomy made great strides in studying and modeling the orbits of the planets, and it became clear that our system is extraordinary. And it's not because there is an Earth inhabited by intelligent beings, and it all started with Jupiter. Its orbit deviates too much from a circle. Its elongation, scientifically known as eccentricity, is 3 times that of the Earth. We know that it is very difficult to break the orbit of a celestial body when it has a large mass, and the more mass, the heavier it is. In the early days of the solar system, when the young planets were still emerging from the protoplanetary disk, they had smooth, circular orbits. Gravitational interaction with some object was required to achieve their elongation. Jupiter has 318 times the mass of Earth and 2.5 times the mass of all the other planets in the solar system. It takes huge gravitational interactions to expand that orbit that much. But with whom? What planet could have been so massive that it could have impacted Jupiter? Uranus and Neptune are also strange. By calculation, they must have been formed in their present location for longer than the protoplanetary disk could have existed. The only reasonable way out of this paradox is that they first formed much closer to the Sun and then moved farther away. But the big mystery of our system is Mars, and indeed all rocky planets. The farther a planet is from the Sun, the more massive it is. Finally, the farther away from the star this or that part of the protoplanetary cloud, the less matter in this part of the cloud moves outward under the influence of the radiation of the star and its wind. On the face of it, this is true. Mercury is 15 times lighter than Venus, and Venus is 1.18 times lighter than Earth. But Mars, this is where the pattern breaks down. It's 9 times lighter than our planet. Of course, some of the problems can be solved by saying that Jupiter's gravity has pulled some of the planet beyond Zemalea away from Mars. These are the small bodies from which the Earth group planets were formed. But calculations show that instead of Mars, there should have been a planet comparable to Earth, or at least half the size. This is not a matter of calculation or theory. Mars is located in the habitable zone of the solar system. If its atmosphere were at least comparable to Earth's, it would retain enough heat to make the Martian climate similar to Earth's dry climate. But in practice, today's atmosphere is 150 times thinner than ours, and gravity is too weak to support a denser crust. And that's a fact. Apparently, if Mars were 5 to 9 times larger than it is now, the 4th planet in our system would be habitable. Observations of other planetary systems show Earth-sized planets, with Venus, Mars, and Mercury, being extremely rare. In other planetary systems, the mass of rocky worlds is usually much greater than Earth's. That's why they're called superpowers. Does it turn out that all of our Earth group planets are anomalies of some kind? Astronomers Michael Brown and Konstantin Batygin believe, and most of the world's scientists agree with them, that there is a super-Earth in the solar system. It is simply incredibly distant from the Sun, hundreds of times farther than Earth and 10 times farther than Neptune. Of course, protoplanetary disks of this size have never existed in our system. In other words, this super Earth got there by exotic means after it formed near the Sun. In other systems, such an event as the movement of planets to or from their star is a strange phenomenon. A whole class of planets called hot Jupiters exist only because of the wandering of their stars. The Sun doesn't have any. Gas planets cannot appear near stars. However, once formed, the gas giant may lose its orbital stability. It can collide with Earth group planets, gradually slowing its rotation around its star. As the speed of rotation decreases, the planet begins to describe increasingly narrow circles around its star. At the same time, its gravity ejects objects it encounters on its way out of the system. Therefore, hot Jupiters often leave their star without Earth group planets, and they themselves come so close to it that they heat up to thousands of degrees. A clear picture emerges from such a scenario. Our system was also originally quite different. Giant planets were not necessarily born where they are today. Astronomers have created some fairly detailed mathematical models of the motion of solar system bodies and discovered something unexpected. From the point of view of celestial mechanics, the original region of Jupiter's formation, which would correspond to its present orbital elongation and position, is only 3.5 AU from the Sun, or 3.5 times the present distance between Earth and the star. However, Jupiter is currently at an average distance of 5.2 AU from the Sun, which is 250 million kilometers. But how did it get there? This is where computer modeling comes in. Collisions with the Earth slowed down Jupiter's rotation around the Sun, causing the planet to move more slowly along its orbit and thus begin to approach it. On its way to the Sun, Jupiter's gravity dragged Saturn along with it. Earth group planets form more slowly than the gas giants and stop forming after them. So, Earth and Mars are lucky in a way. If they had already existed then, they would have been in great danger. Jupiter stopped just 1.5 astronomical units from the Sun, so it was a little closer to Mars. The formed planets would have gotten too much momentum from their gravity, and their orbits would have been too unstable. Most likely, they'll just fly out of the system. However, the transit of Jupiter brought serious problems to the future rocky planets. Its gravity did its job. The gas and dust from this part of the protoplanetary disk was literally swallowed up by Jupiter. He had to eject part of the planet Zemlya out of the system. The region where Mars formed was so poor in material that it received far less material than Earth. But why did Jupiter not stay within an AU and a half of the Sun, but turned around and went back? There's only one explanation. Moving behind Jupiter, Saturn entered a resonant orbit with Jupiter at a certain point. That means that the period of 2 revolutions of Saturn around the Sun was equal to 3 revolutions of Jupiter. 3-to-2 resonance. Orbital resonance means that bodies regularly encounter each other. The gravitational interaction between the two is dramatically increasing, and their orbits are undergoing major changes. The connection with Saturn pulled Jupiter back in time. After all, what would happen if the largest gas giant did not stop at a distance of 1.5 astronomical units, but reached one? You mean up to Earth's orbit? Maybe in that case there would be no one to ask. Earth will be as small a planet as Mars because Jupiter's transit won't leave much material to form it. Even if it had life on it, it is unlikely to have been as advanced as it is today. It is believed that Jupiter is the patron saint of the Earth. Today it protects our planet from asteroid impacts. In this case, Saturn is the savior of the Earth. Such a journey of Jupiter could not help but affect Uranus and Neptune. At first, they were less than 17 AU away from the Sun. The wandering of Jupiter and Saturn finally threw them into distant orbits. They remain there to this day. Uranus shown at mid-19 AU and Neptune at 30. And what about the super-Earths of the solar system? They're the most massive class of planets in the Milky Way, but they're not in our system. They form faster than the smaller Earth group bodies, so when Jupiter's migration begins, they could already be in our system. In that case, they were in for an enviable fate. They should have been destroyed by falling into the Sun. In the rocky planetary regions of the solar system, the remaining material of the protoplanetary disk was too small to form a second-generation super-Earth. In all, it took the formation of 4 planets with masses about half that of Earth. But it's not all smooth sailing. Almost all computer simulations of early solar system transitions show that its current configuration afterward is unlikely. At best, the planets should be in different orbits with slightly different elongations. They understood this problem for a long time, until they tried to include more planets in the modeling. It turns out that if the early solar system had not 4, as it does today, but 5 giant planets, the probability of the system forming in its current form increases significantly. In fact, about 4.6 billion years ago, there were almost certainly 5 such planets, and the 5th planet was an ice giant like Uranus or Neptune. In addition, astronomers Batygin and Brown, who have hypothesized a 9th planet orbiting at a distance of hundreds of astronomical units from the Sun, note that it is probably a large object, or one that was once flung there during the Great Jupiter voyage. Back. Thus, almost the entire architecture of the solar system was determined by events before the Earth existed. In place of Mercury, Venus, our planet, and Mars, there could be a super-Earth right now. Perhaps more than one. Back then, there were 5 giant planets, not 4. The chaotic migration of Jupiter and Saturn destroyed all the ancient super-Earths, ejecting them into the Sun, and simultaneously ejected the 9th planet of the present solar system. At the same time, Jupiter and Saturn themselves have moved farther away from the Sun, and Uranus and Neptune even farther from the light. It turns out that the migration of giant planets is the main mechanism governing the scenario of planetary system evolution. Those with hot Jupiter can usually lose Earth group planets and habitability. Their giant planets are so hot because their journey ended close to their star. They had no Saturn of their own to turn them around. The continued presence of giant planets in near-stellar orbits makes it less likely that a smaller rocky planet will be in the habitable zone. But there are systems where the migration of giant planets has not occurred at all. In this case, they form a super-Earth in orbit near the star. The best-known such system is TROPIST-1, 40 light-years from Earth. It is not yet known how habitable they are, but if they are, such systems could have more than 1 and sometimes more than 2 habitable planets. Whether this is true or not, we'll be able to find out in the coming years thanks to the soon-to-be operational James Webb Telescope. Before the discovery of massive exoplanets, it was widely believed among scientists that the solar system was the most favorable place for the formation of Earth group planets and life. But today, knowing the great migration of Jupiter, this hypothesis no longer seems reasonable. Earth and Mars escaped destruction and were not miraculously ejected into interstellar space. It appears that habitability in our system has been unusually difficult, and the number of habitable planets here is much lower than would be expected in quieter systems.